Before we can start talking about differentiation, integration, and parameterization in three dimensions, we have to start by talking about the Cartesian plane in three dimensions. So instead of having a two-dimensional sort of relationship, now we're going to have a three-dimensional relationship between variables. So instead of just an xy plane, now what we have is we have an xyz plane. Before we had quadrants. Now we have octants. And generally when we try to plot coordinates in three dimensions, we're going to use the right-hand rule. So what that means is that we're going to have an x-axis, a y-axis, and then a z-axis. And think of this as like the corner of a room. And this is our x positive, this is y positive, and this is z positive. And in subsequent examples, we're going to see how to be able to plot in three dimensions. Similar to what you learned in pre-calculus, instead of an ordered pair, we have an ordered triple. And an ordered triple is the ordered triple x, y, z. And as such, what we're going to do is we're going to go to, on the x-axis, either positive or negative first, the y-axis either positive or negative, and then the z-axis either positive or negative. Subsequently, there are a number of formulas that we can utilize, very similar to pre-calculus, to be able to work within the Cartesian plane in three dimensions. So, we have a distance formula. The distance formula between 2 points is given as x2 minus x1, y2 minus y1, z2 minus z1, all squared, and then we take the square root. If you were to cover up this part, that would actually be the distance formula in 2 dimensions. However, we're looking at the distance formula in 3 dimensions. Very similarly, the midpoint of a line segment in 2 dimensions would just be x1 plus x2 over 2, comma y1 plus y2 over 2. However, since we're in 3 dimensions, then we're going to add this z1 plus z2 over 2. And then finally, if we want to look at a sphere instead of a circle in 3 dimensions, then what we're going to be doing is we're going to be adding in z minus z naught square, and that's still going to be equal to the radius squared. And again, think of this in 2 dimensions. In 2 dimensions, you just had these 2 components, x minus x naught squared, y minus y naught squared is equal to r squared. However, in 3 dimensions, in other words in calculus 3, now we have this z minus z0 square, or z naught. So, predicated upon all this information, let's take a look and work through a few examples together where we can look at the Cartesian plane in 3 dimensions. So let's consider the ordered triples p equals 1, 3, negative 4, q is negative 2, 3, 1. We want to plot the points, we want to find the distance, and then we want to find the midpoint. So, plotting the points, here's our 3-dimensional plane. Now this is x plus, this is y plus, and this is z plus on the axes. I want you to notice that we also need an x negative and we also need a z negative to plot this correctly. So I'm going to extend the x-axis, and this is our x minus. I'm going to extend the z-axis, and this is our z minus. And we're just going to plot the points right on the plane. So if I was to plot the point 1, 3, negative 4, here's how I would do that. I would go 1 in the positive direction. I would move 3 units in the positive y direction. And what you can almost do is you can almost think of this as like a point that's on the floor. Now, we want to go below the floor because we have to go 4 down. So we're going to go 1, 2, 3, 4. We're just going to trace this down 4 units. And so this is our point P. We want our point Q, negative 2, 3, 1. So we're going to move 2 units in the negative x direction, 3 units in the positive y direction. And again, just like we did before, we're going to kind of line these up on the floor. And then finally we're going to move up 1 unit. And so we end up with the point, even though it looks like it's in the floor, it's actually above that. Okay, so that's going to be our point Q. It also asks us to find the distance of that line segment. So this is letter A. Letter B, we recall the formula for the distance. So I'll write it out that the distance d is going to be equal to the square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square, all under this radical. And if we go back up here, let's think of these as x2, y2, z2 as the terminal points. And then let's think of these as x1, y1, z1 as the initial points. And we could just substitute those directly back into the formula. All right, so if we were to do that, the distance d is going to be equal to the square root of negative 2 minus 1 square plus 3 minus 3 square, and then plus 1 minus a minus 4 squared. And then we just go through and compute that. Negative 3 squared is 9. 3 minus 3 squared is 0. 1 minus a minus 4 is 5 squared. And we end up with the square root of 34. In this course, I'll ask that unless I specifically ask for an approximation, to keep your answers in the exact form. All right, so I don't need the decimal of 5 point whatever it might be for the square root of 34. The final thing that we're asked to do is we're asked to be able to find the midpoint of the line segment. So all we're going to do is we're just going to add the x, y, and z components, and then we're going to divide by 2. So for C, the midpoint is going to be equal to, so remember we had negative 2 and 1. All right, so we have, 1 plus negative 2 over 2. And then we had 3 plus 3 over 2. And then finally, 1 minus 4, or 1 plus a negative 4 over 2. And this is going to yield the point negative 1/2, since that's going to be negative 1 over 2. 6 over 2 is 3, and then negative 3/2. And so that's some of the most basic geometry that we're going to be looking at with respect to our Cartesian plane in 2 dimensions. Now, another thing that we're going to be asked to do is we're going to be asked to work with planes and also different inequalities in 3 dimensions. So let's take a look at some of these types of problems. So for this example, we're to graph the following planes, and I'll just do these individually. So these are all separate planes. So let's think about what this means. Z equals negative 2 means that x can be any real number and y can be any real number. So we're going to say x is a real number and y is a real number. The only thing that we know is that z is going to be equal to negative 2. All right, so if I was to plot this on a 3-dimensional plane, and again, this is x plus, y plus, z plus, and of course we need a z minus because z is negative 2, then we're just going to go down 2 units, and we're just going to draw a plane that passes through negative 2. So this is our plane z equals negative 2. Now technically, this plane extends indefinitely in all directions. All right, so just think of this as an infinite piece of paper that's basically slicing through z equals negative 2. However, for convention, all we're going to do is we're just going to write it as z equals negative 2. And we're just going to write a plane. All right? And it's all the points that are in there, so we can shade it in. That's perfectly fine. It's just understood that it's going to be z equals negative 2 is all the points that are within that plane. All right. A second example, y equals 4. So again, here's our plane. We have x positive, we have y positive, and we have z positive. We're going to go to 4. And again, this doesn't say anything about x. It doesn't say anything about z. All it says is that y has to be equal to 4. So we're just going to draw a plane. And again, think of it like a piece of paper. and that piece of paper is slicing right through the point y equals 4. And just like the previous example, this just extends indefinitely. So this plane just keeps going forever in the x direction as well as the z direction. All right, but for convention in Calculus 3, we're just going to write a sample of that plane, and we just understand it to go on forever, similar to a line in 2 dimensions. All right, a few more examples. So let's make some room here. And again, just making some room, so one moment. We have x greater than 0. All right, so we have to be careful with this one. So here's our plane, and this is x positive, y positive, z positive. X greater than 0. So that means that we need to first of all plot the plane x equals 0. So first of all, we're going to plot x equals 0, and we're going to have one caveat to that. Now x equals 0 means that y and z can be anything. All right? So essentially x equals 0 is going to be right through the yz plane. All right? So this is the plane x equals 0. All right? And I drew this one hyphenated because we're actually looking for x greater than 0. So since x is greater than 0, remember the greater than means that it excludes the points on the plane. All right. So because we exclude the points on the plane, we're going to draw a hyphenated plane, and then we're going to shade, because it's x greater than 0, we're going to shade all the area to where x is positive, or all, in this case, all the volume. All right? So when we shade this, it's going to be all of this volume. Okay, so it's a lot of volume because we said that x is going to be greater than 0. A fourth example, z less than 1. So again, here's our plane, our Cartesian plane. We have x positive, y positive, and z positive. We're looking for z less than 1. That was what we're asked to find. Right? So to do that, we're going to plot the plane z equals 1. And again, it's going to be hyphenated because we want less than, not less than or equal to. Let me erase this. Right. And since it's less than 1, we're going to shade all the volume below that plane. Okay, so anything that's lower than z equals 1 is going to be the volume for this. Okay. And then finally, we have a couple absolute values to graph. So let's graph those. So we have absolute x less than 3, absolute y greater than or equal to 2. So absolute x less than 3. Now, this means we have to be careful with this because this can be written as an inequality. So what this really means, if I was to remove the absolute value brackets, is that -3 is less than x, which is also less than 3. It's a compound inequality. Okay, you may remember that from pre-calculus. To remove an absolute value, you just make it a sandwich if it's a less than towards the absolute. And what we're going to do is we're going to plot this, but we have two planes to plot now. So this is x plus, this is x minus, and then we have y plus and z plus, excuse me. And we're going to plot two planes. First of all, we're going to plot x x is equal to -3. So we're going to go over here. And we're going to plot this plane. And then we're going to go over here, and we're going to plot x equals positive 3. And what you can think about is that since x is sandwiched between here, it's almost like we have a cube of volume that's going on with this. So just think of this as we're connecting the dots here. Right? And all the volume is between -3 and +3 in the x. Okay, so what we're looking at is essentially, think of it like a die if you're throwing a die or a solid wood cube. Right? And that's what we're looking at. Now, of course, remember, z and y are going to extend indefinitely in both the directions. Okay, so it's like a cube, except it's going to extend forever, and the only boundary is between x. Okay, so think of it getting infinitely tall, like a skyscraper that you can't see any longer, except that it's going to have a certain width to it. Right. The last thing that we're asked to graph is absolute y greater than or equal to 2. So if we graph that, first of all, we might want to interpret that. And what that means is that y is less than or equal to -2, or y is greater than or equal to 2. And if you don't believe me, plug in some numbers that are less than or equal to -2 and see if it makes the inequality valid. Okay, that might be the best way to do it if you don't remember those rules from pre-calculus, is to go through, just pick a few test values and see if those test values work or don't. That means we're going to plot these two planes to start. They're going to be solid planes because they're underlined, so we're going to include the bounds. All right, so we have, so this is going to be y positive and this is y negative. Let's plot y equals 2, and again, solid bound. And let's plot y equals -2. Again, solid boundaries. Okay. Now this time, it says that y is less than or equal to -2, or y is greater than or equal to 2. So that means it's everything to the right or on the plane. All right, so we're looking at this volume, and that represents y is greater than or equal to 2. And then everything to the left of the other plane, or on the plane, okay, so I'm going to shade on the plane and then everything to the left of it, okay, that's going to represent y less than or equal to -2. Okay, so basically we have a space in between those two planes, and again, those two planes run on indefinitely. So hopefully this is a good explanation of the rudiments of the 3D plane, and also how we're going to plot a few of the things on the plane.